Okay, this is our fourth and final part of our lecture video for Friday, March 24th, where we begin our discussion about the next class of aqueous reactions that you'll see in Chem 210, which is a gas evolution reaction. So I've thrown the definition of gas evolution reactions up here on the board, where I state that a gas evolution reaction is any aqueous reaction that generates some kind of gaseous product. So a precipitation reaction is an aqueous reaction such that a double displacement of ions creates a solid product or an insoluble precipitate product. Here, an aqueous reaction that generates any kind of gaseous product is what we call a gas evolution reaction. And gas evolution reactions can occur via two different kind of mechanisms or ways. Like there's two different pathways in which a gas can be evolved or created as a result of some aqueous reaction occurring. So there is firstly the direct formation. So our gases are formed as a direct result of some kind of displacement. And in gas evolution, we will see gases evolved in a lot of single displacement reactions, which we'll call redox reactions later. But for now, we're going to focus kind of on double displacement. And the best example of this is anytime we look at a reaction that involves a reaction of a sulfide ion plus any kind of hydrogen ion. So anytime you have sulfide ion in the presence of something that put H plus into solution, you are looking at the formation directly of hydrogen sulfide gas, H2S gas. This gas is what's going to give a kind of rotten egg or garbage smell. Very, very stinky. Not something we ideally want, but anytime you have a reaction, and I'm going to show the net ionic equation that would make this, you always have some kind of H plus in solution reacting with our sulfide ion in solution to directly make or generate hydrogen sulfide gas. So any reactions of the sulfide ion and H plus is going to give us a gas evolution. Now the other way that gases can be evolved or made from solution is as an indirect result of a double displacement. So gases can also be formed as an indirect result of our aqueous displacement, where first our double displacement, like we saw in precipitation, happens first, and then almost immediately or instantaneously after that double displacement occurs, one of those resulting products that is made is so inherently unstable that it immediately decomposes into some kind of gaseous compound. So any ion that you need to be aware of in aqueous reactions that will form potentially an unstable, insoluble, not insoluble, an unstable aqueous product is we have any kind of carbonic acid being formed, if we have any kind of sulfurous acid being formed, or if we have ammonium hydroxide being formed. All of these are unstable intermediate products because they are made in some kind of middle step with the final step being the generation of these gases. So let's look at a particular aqueous reaction and let's see what happens when we might have carbonic acid, sulfurous acid, or ammonium hydroxide formed as one of our potential products. So let's look at ammonium hydroxide. This is something that we saw in our 9 solution problem on Tuesday. We looked at a reaction of ammonium chloride and sodium hydroxide. And just like I did with precipitation, I'm going to split each of these up into their respective ions so that I can very neatly predict what my double displacement products are going to be. So my anions are now going to associate with the opposite cation. This is going to form, if I think about what's going to happen when I make an Na cation come together with a chloride anion. These are equal and opposite, so we form an 1-to-1 sodium chloride solution. By now I know that sodium chloride is indeed a soluble product because I've got my chloride anion and I don't see any of my exceptions, which would be silver, mercury, or lead. Plus we've all seen table salt dissolve in water. And then I now have my ammonium ion coming together with hydroxide. Since we have a ammonium with +1 and a hydroxide with a -1 charge, we need these to come together in a 1-to-1 proportion. So this makes ammonium hydroxide, and all ammonium compounds are soluble. And what we have formed here is one of our unstable intermediates. Meaning that if I were to think about what happens to the ammonium hydroxide, let's look at what its potential decomposition could generate. So for those of us in the 11 a.m. lab, we were able to smell the product of this reaction, and it vaguely smelled kind of like a clean bathroom is what a lot of people said. And that's because it smells like the main ingredient in Windex, which is ammonia, NH3 gas. And if we think about what happens here, if I'm decomposing this, I've used an N and 3 of my H's, leaving behind an H and an OH, which is going to come together and create H2O liquid. So if I were to write the full and complete reaction, I would have this reaction shown in 2 steps. Ammonium chloride reacting with sodium hydroxide to form sodium chloride and ammonium hydroxide which has sodium chloride in solution still, and then the resulting decomposition products of our ammonium hydroxide, which was our ammonia gas, and H2O liquid. Where all of this here, this is showing the intermediate that is formed and then ultimately decomposed. So this is the entire reaction showing both steps, steps 1 and then 2. And if I wanted to write I'm going to write total reaction, meaning just showing reactants and then products. This would be my ammonium chloride reacting with sodium hydroxide to create just our total final products, which was our sodium chloride, and then the decomposition products of ammonium hydroxide, which was ammonium gas and liquid water. I could also write a complete ionic equation. So that is where everything that is in the aqueous phase from my total reaction will now be dissociated into its ions. So I would have NH4 plus and Cl minus coming together with Na plus and OH minus to form Na plus and Cl minus ions, my ammonia gas, and then liquid water. So any of my non-aqueous products, I do not write in their dissociated ionic form. I could also take this a step further and write my net ionic equation, which eliminates my spectator ions or any ions that didn't seem to do anything interesting upon the reaction of these two reactants. And if I look for these in my reaction, I've got sodium cation and then chloride anion, which really didn't do anything. These are my spectator ions. They are still present in the beaker. It's just when I write my net ionic equation, I want to show exactly what ions were responsible for the formation of something interesting. Here are gas evolution. So this would be the reaction of ammonium ion with hydroxide ion to create ammonia gas and liquid water. So let me write out for you our general unstable aqueous intermediate decomposition products. So we said carbonic acid. This is always going to decompose into carbon dioxide gas and H2O. Carbonic acid is found in all of your soft drinks, and when you depressurize your soft drink by opening your can or your bottle, the fizzing you see is the immediate decomposition of that carbonic acid, which was forced to be in solution because of the pressure of the bottling or canning. And once you release that pressure, it can freely decompose and it releases CO2 gas and creates liquid water as a result of that decomposition. Sulfurous acid, this is in fact so unstable that it's only theoretically proposed. We have never been able to see sulfurous acid in solution before in the lab. This is going to generate sulfur dioxide gas and liquid water. And then of course ammonium hydroxide will form ammonia gas and liquid water. So let's think about anything that could react to form each of these intermediates that are unstable. So anything that contains a CO3, like carbonate or bicarbonate, reacting with H+, those can generate carbonic acid. Same deal with the sulfurous acid. That can be H+ and our sulfite ion, our bisulfite ion, and then the ammonium hydroxide, this is H+. Well, no, okay. It's anything containing OH- plus the ammonium ion. So keep an eye out for reactions that have sulfides, like so. And also keep an eye out for these unstable intermediate decompositions that involve these ions here with H+, except for ammonium, of course, which is with the hydroxide. This is their decomposition results, and these are what you're going to write in your complete and net ionic equations. Okay. So when we come back from break, we will practice writing out more complete and net ionic equations for gas evolution reactions. And then from there, we will move on to our next type of aqueous reaction, which are called neutralization reactions or acid-base reactions. So that is it for today. Have a lovely spring break, everybody. I will see you all next Tuesday for our second midterm, and I hope you get some good rest this coming week.